Welcome to this talk. My name is Matthias Oberlechner, and I'm very happy to present to you joint work with Martin Bichler and Maximilian Fichtl on the computation of base Nash equilibrium strategies in auction games. So let me first start with the setting that we are interested in. So we consider auctions because, first of all, auctions are very helpful in understanding more complex environments in economics. And second, auctions are actually used very often in practice. So we have, for instance, spectrum auctions, or we use auctions to sell financial products and stuff like that. And if we want to analyze auctions, then we often model them as continuous type and continuous action incomplete information games. And we use the solution concept of base Nash equilibria as a model of how rational agents should or might behave in these settings. But the problem here is that if we deviate from benchmark models, the equilibrium analysis can get very challenging. And naturally, we want to know, well, how can we derive these base Nash equilibrium strategies in such settings where an analytical solution might not be known? And before we dig deep into this question, let me first introduce the model in more mathematical terms. So we model our auctions as these incomplete information games, which consist of 5 elements. I think it might be more instructive to have a look at a small example to explain this definition. So let's consider here a single item that we want to auction off in a, let's say, first price sealed bid auction. So we have here our set of agents I, so these 2 bidders who participate in this auction. And the way we model this is the following. So in the first step, agents observe their valuation for the item. And in our model, we draw some values from the valuation space according to the joint prior probability distribution. And after the agents observe the valuation, they submit a bid. And this bid is an element of the action space of the agents. And then after submitting the bid, the item is allocated and the bidders observe their utilities. So in that example, agent 1 would have a utility of the valuation minus the bid, while agent 2 has a utility equal to 0 because he or she did not get the item. So we have this setting we're interested in, and now we want to know how the base Nash equilibrium strategies look like in such settings. And when we talk about strategies, specifically about pure strategies, what we mean are functions that map valuations to actions. So each agent has a strategy, beta, which is a function that maps the observed valuation to an action. So how much they should bid in an auction. And if we have these strategies of all agents, we can compute the expected utility for all agents. And naturally, as these agents are rational and want to maximize their utility, but as their utilities also depend on the opponent strategy, the solution concept that we are looking for is the base Nash equilibrium, which is basically a strategy profile where no agent has the incentive to deviate unilaterally in order to improve the expected utility. So we know the setting, we know what we are interested in. Now, how can we compute these equilibrium strategies in such auction games? If you look at textbooks, for instance, people often use first order conditions to derive some ODE, which you can solve to get the equilibrium strategy. But this mostly works in very simple settings where bidders are symmetric, valuations are independent, and stuff like that. But if you look at more complex settings where, for instance, valuations are interdependent, you might end up with a PDE that we do not know in general how to solve. So one other way would be, well, we could use equilibrium learning to derive these equilibrium strategies. But here we have 2 major problems. First of all, we know that already in the simpler complete information setting, we know that the dynamics might not lead to Nash equilibrium in all settings. And we know that even in very simple settings, such as bimatrix games, for instance, and the learning dynamics can lead to arbitrarily complex behavior. And the second point here is, it is not even clear how we would apply these methods to continuous incomplete information games, because here we are looking for some function, for some bit function of unknown shape, which is in some infinite dimensional strategy space. And what I want to focus on in this talk is a procedure on how we can answer the second part, or the second part of these problems, namely how we apply learning methods to such auction games. And our approach basically consists of 4 steps. So first we start with the original auction game, modeled as a incomplete information game as introduced before. And then we use distributional strategies and the discretization of the spaces to end up in some approximation game where we then can apply these standard learning techniques to compute equilibria. So let's start with the distributional strategies. They were introduced by Milgram and Webber in the 80s, and the main idea is that instead of functions that map valuations to actions, we look at probability measures, which assign probability to valuation action pairs. And the formal definition is that a distributional strategy is a probability measure over the agent's type and action space. And it has to satisfy some marginal condition, which simply ensures that the probability distribution over the valuations is consistent with the prior probability distribution given by the incomplete information game. Right. And if we have such distributional strategies, we can again compute the expected utility and can use the same definition of the base Nash equilibrium as we've seen before. Okay, but now we simply move the problem of finding some equilibrium function to some equilibrium probability measure, but we are still in some infinite dimensional space. So we have to discretize our problem somehow in order to apply numerical methods to that. And the way we do it is by discretizing the spaces. So we allow agents only to have the discrete valuations and to only submit discrete bids in these auctions. And the reason why we use distributional strategies is that they are very easily applicable to this discretized setting. So instead of a probability measure over the continuous actions and type spaces, we now have a discrete distributional strategy, which can be represented as a matrix, for instance, where each entry of the matrix denotes the probability of a discrete valuation and action pair. And similar to before, we can still compute the expected utility and can still use the same definition for our base Nash equilibrium. So that hasn't changed much. Okay, and now if we combine these 2 approaches, we end up in an approximation game. So the discretized incomplete information game with these distributional strategies, or in that case, then these discrete distributional strategies, they define a complete information game, which we call approximation game. The complete information game, again, consists of the same set of agents. The action space of this complete information game is now the set of discrete distributional strategies, which is a compact convex subset of R to n times m. And the utility function is simply the expected utility we've seen before. And it's important to observe that this utility function is linear in the agent's own strategy. So we have a very well-behaved complete information game, our approximation game. And it's also easy to see that if we have a Nash equilibrium in the approximation game, we automatically have a base Nash equilibrium in discrete distribution strategies in the discretized auction game. And the same holds for approximate Nash equilibria and approximate base Nash equilibria. And if we have approximate Nash equilibria, this epsilon is very easy to compute in the approximation game because we only have to solve a simple LP to derive this epsilon. But now what we want to know is, well, if we have some approximate Nash equilibrium in the approximation game or in the discretized auction game, does this tell us anything about an equilibrium in the original continuous auction game? And this is our main theoretical results. So we could show that an epsilon-based Nash equilibrium of the discretized auction game induces an approximate base Nash equilibrium in the original continuous auction game. And this approximation has some additional term which depends linearly on the discretization of the spaces. For this result, we had to make some assumptions, but these assumptions still include many settings such as single item first and second price auctions, all pair auctions, and stuff like that. So this is very helpful because now we know we can focus on computing Nash equilibrium in the approximation game because this induces an approximate base Nash equilibrium in the auction game. And to compute Nash equilibrium in this approximation game, we can use standard techniques from equilibrium learning. So here we focus on first order methods. One example would be simultaneous online dual averaging. So here in each iteration, each agent computes the gradient of the utility function, then uses this information to update the strategy somehow. So here the update rule we used is dual averaging, but you could use any other methods if you want. In our numerical example, we use the different versions of dual averaging and also mirror ascent and the Frank-Wolfe algorithm. And so this explains our procedure. Starting with the auction game, we discretize spaces, use distributional strategies to end up with some complete information approximation game, where we then apply our learning methods. And one very important result here is, and that's taken from Matthias and Su in 2019, and that says that if we apply dual averaging in our approximation game and the sequence converges to some strategy profile, then this limit point is a Nash equilibrium in the approximation game. And this is very helpful for us because we start in the approximation game with some random initial strategy, then we apply dual averaging, and the method converges to some strategy profile, then we know this is a Nash equilibrium. And by our main result, we know this induces an approximate base Nash equilibrium in the auction game. So we kind of have an exposed certificate for our computed solution. We don't have to verify the induced strategy in the original auction game. That is very helpful. One thing I have to mention, which is one downside of this approach, and that is scalability. If you recall the expected utility, we compute using these discrete distribution strategies. You can see that we sum over all possible utility outcomes. And this means we have to sum over n times m to the power of number of agents times number of items, numbers basically. And n is here the discretization of the valuation space, and m is the discretization of the action space. So we can see that if we have a high number of agents or a high number of items, this explodes basically, and we run into issue regarding runtime or memory and stuff like that. So we are restricted to auctions with a small number of bidders and items. But if you look at the literature, the most important settings are settings with a small number of bidders and items, because only with a few bidders, these strategic interactions really have an influence. And these are the interesting settings we want to understand. Okay, so let's talk briefly about our numerical experiments. So we applied this procedure to many different mechanisms. Here we can see a few single item auctions and even small combinatorial auctions where we know the analytical Bayes Nash equilibrium so that we can compare our computed solution with the analytical one. But here we have settings which are maybe even more interesting, because there we do not have analytical solutions. And these are settings where our method can be very useful and shows us how equilibrium strategies might look like in the original continuous auction games. Okay, so that's it from my side. I want to briefly mention the key takeaways from this talk. So first, we introduced a fast numerical tool for auction models, for small auction models, basically, that is based on the use of distributional strategies and discretization of type and action spaces. We have an exposed certificate for some auctions, so we know if we have if we converge in our approximation game, we have some approximate Bayes Nash equilibrium in the auction game. And our empirical results indicate that indeed in many auction settings, or in all auction settings we looked at, we can compute this equilibria. So we do converge to some strategy which approximates the analytical equilibrium strategy. But these are only empirical results, so we do not have convergence results. So we are still looking for the underlying structure of these auction games, on why these methods work so well in these settings, and why we do not observe some arbitrary complex behavior as we can see it in some complete information games. So that's it from my side. Thank you very much for listening. If you are interested in our paper, here is the link to the version on arXiv, and you can also look at the implementation, which is available on GitHub. Thank you very much.